or contents. Any questions? Any problems? Yes.
Here's a question on last year's homework, something about create a parse tree for ABAB. And I was wondering, how do you approach that? Do you just kind of randomly try different combinations, or is there a systematic way to try and get to that ABAB at the end?
Yeah, that was kind of a difficult question. A lot of students didn't get it. Yeah, there is no systematic way of coming up with a parse tree, but you have to just try different solutions.
Okay.
Anybody got the solution? Oh no, I have already uploaded the solution, so you have the solution. This one?
Yes.
Where is it?
Number 4 at the top of that page. Actually, second page, where it says problem 2 out of 3, it's number 4 part. Show that this grammar is ambiguous.
Oh yes. No, if you want to have, if you want to answer that question, then no, you don't really have a methodical way of having two different parse trees. But given a derivation, we can definitely see how a parse tree is created. So this solution I have it, right? Yes.
Are we supposed to do this one or the 17, 2017?
Really sad. This one solution is already there. What will you do?
Oh, I see.
You are supposed to do the other homework. Homework 1, summer 2017.
Just one check.
Any problems with this homework? I think this homework is much more easier than the earlier homework that I did. Yes, very straightforward. This one is just first and follows it. So just follow the rules, you'll get this. Anybody done with the first project? You passed all the test cases? Did you take into account comments? Comments?
Yeah.
So one important thing is that I will have, so the test cases that I've given you, I won't use that for grading. There is a separate grading test case, but that particular test case set has all possible things that can occur. But in the test case that I will have, it will be bigger test cases. You won't see surprises in that test case. So whatever different combinations and things that I have in the sample test case that I have given, I will have the same things there, but in larger numbers. Right? So these will be bigger test cases, and so one thing that you have to take into account is that in test cases there will be comments, right? Slash slash or slash star. Those comments you have to skip. Right? So that is one program that you have to write, skipping comments. I think I have one or two such things in the sample test case that I have given you. There are some test cases with comments. Are there or no? There are not? Okay, maybe then you don't need to. I'll check, I'll let you know. Okay, so let's continue our discussion. We are talking about this semantics of assignment. Assignment semantics. So let's redo the example that we did, and we will show some, or we'll talk about some other concepts from that example. So we had this code, right? We had int star star x and so on. So if we execute the first line, we know that whenever we declare, we have a box and circle diagram for that particular variable. Then since we have it for y, we also have one for y, and we declare z, so we have one for z. Now the trick happens. We execute this line of code, malloc. The moment we execute malloc, we have to allocate certain memory or one line in the RAM. So let's say that is that line, and the address for that line is 0x4. Let's say, assume, right? Now, if we execute that line of code, what happens is that the address of that memory goes into the value of x, right? So you have 0x4 here. So which means if I do star x points to that location. So the value in that location. So value in location 0x4, that is star x. Everybody understands this point, or do you have doubts? Anybody has doubts at this point? No. So then we move on. The second line is exactly same. Same thing should happen. So when we execute the second line, we should have another address which is different from the first one, another memory location allocated, right? And let's say its address is 0x8. Then what should happen is that 0x8 should come into the value field of y, and star y should point to that location. Exact same thing happens. Now we execute this line of code. X equals ampersand y. What should happen? What we said was that we take, so we have to find out what is the address of ampersand y. Let's say we give these addresses adx, ady, adz are addresses corresponding to the location of x, location of y, and location of z. Let's say that is the case. Now if that happens and we execute that line of code x equals ampersand y, then what will happen is we'll remove this 0x4 and we'll replace it with ady. So now star x is not pointing to 0x4, it is pointing to y, the location of y. So star x becomes whatever is the value inside y, and that value is what? That value is an address, right? That value is an address, so which means it's an L value, because with respect to that value a location is associated. So star x now becomes an L value. And what is star x? Star y. So star x becomes star y, which is any value that is in 0x8. Currently nothing is there. So now we do y equals ampersand z. It's the same operation that happens. So instead of 0x8, we will have adz here, and then we will cross that link and have a new link for star y. Same thing happens, right? Now we execute the next line of code, which is y equals star x. What does that do? Y equals star x. What is star x? Star x is the value inside y, so adz, right? And what is the semantics of this assignment? Y equals star x. We will take the value in the location associated with star x and put it inside y. What is the location associated with star x? It's y, right? That is the y location associated with it. And what is the value in there? adz. So we take that adz and put it back in y. So nothing changes. Now we have some more code. We make z equals 10. What will happen if we make z equals 10? Where will the 10 go? In the circle of that box z, right? So now z becomes 10. Now we print star x. What do you expect? What do you expect to be printed? What is star star x? 10, right? Because star star x is star y, and whatever value is inside star y, which means star y now points to z, so whatever value is inside z. So you should expect that it prints 10. Then we did star y equals 100. What will happen? If we do star y equals 100. Yes?
Yeah, that 10 turns into 100.
10 should turn into 100 because star y points to the location where z is. So 10, you remove it and replace it with 100. And then you print z. So you expect that the output will be 100. So this is like a complex pointer based code, right? So initially it becomes very easy to understand pointer based execution when you have this box and circle diagram and you follow the assignment semantics. Then you'll never have problems understanding pointers. So now what happens here is that star y and z are the same location, right? Point to the same location, star y and z. They are called LISs. Star y and z are LISs. So it is when two L values have the same location associated with them. So star y is a L value because it points to a location. Z is also an L value because it points to a location. But star y and z points to the same location. So that's why they are LISs. Now the question is, what are the other ones at the end of the execution? Which other things are LISs?
Star X and Y.
Star x and y. Is there any other? Star star x and star y as well as z, right? So we have star star x, star y, z as well as star x and y. These are LISs. Now you note that we do not have any links to those memory addresses. If we do not have any link to those memory addresses, there is no way we can have access to them. We cannot write code and have access to those memory addresses. Right? So if we cannot have access to those memory accesses, we cannot deallocate them. Right? If we cannot deallocate a previously allocated memory address, that particular memory address we call garbage. So we'll talk about that. So let's talk about memory allocation. So memory allocation deals with how to create new locations and reserve the associated address. So it involves many steps. One of the steps is you have to find a memory that is not currently reserved. How do you do that? We won't discuss here. We will discuss in operating system class. How you do how do you find a memory that is not currently reserved? You will have to talk about paging, segmented paging, and all this. Then either associating that memory with a variable name or reserving the memory and returning the address of the memory. That is the second step. So either if you have a local variable, then you associate that memory with a variable name, or if you have a malloc, then you reserve that memory and return the address of the memory, and you associate the address with another name. Right. So that is those are the steps for memory allocation. Then you have to do memory deallocation. What is memory deallocation? How to release locations and associated addresses so that they may be reused later in program execution. So these two are very important problems, and they are part of the memory management unit of an operating system. Right? So in the program language class, we won't really discuss this, but we need to discuss what happens as a result of memory allocation and deallocation. What happens when deallocation is not done properly? What happens when allocation is done but deallocation is not done? So we are interested in those things. Right? So let's try to understand what are the different types of memory allocation. We can have global allocation. If you do global allocation, where is the memory selected from? Global memory allocation. Global data, where does it go? Does it go in heap? Global data. Where does it go? Hmm? Does it go into the heap? That's what I'm asking. She also said.
Oh, yes. I think it does.
Anybody else? Does it go into the stack? Global data, remember, index, global. It doesn't go in any of the stack or heap. It just goes into the RAM. Right? So RAM means it's a separate memory allocated for just global data. So whenever you run a code, run a program, you have to allocate memory to 4 things. I think I have said this in this class as well. So you allocate memory to the code, you allocate memory to the global data. So this is part of the base and bound, like this is part of the total memory allocated to the program, right? So you allocate RAM to the global data, you allocate RAM to the code, you allocate RAM to the stack as well as heap. So you don't keep stack and heap, you don't keep global data in stack and heap. You keep it in a separate memory location in the RAM. So allocation is done once, just before starting to execute the program. You do allocation and you never deallocate global data unless the program ends. Right? When the program ends, you deallocate. But while the program is executing, you cannot deallocate global data. Once it is allocated, it is done. Then you have stack allocation. So stack allocation is associated with nested scopes and function calls. Reserved memory is automatically deallocated when you go out of scope. So what is stack for? What do you keep in stack?
Variable.
Variables. What type of variables? Pardon? Local variables. You keep local variables in stack. What else do you keep in stack?
Function frames.
You keep function frames. Function frames means the start address of a function and also the local variables used by that function. Right? So those things you keep in stack. Now stack is dynamic, which means it changes size. So what happens is that this reserved memory in the stack can be automatically deallocated. It can be allocated, deallocated automatically. It is automatically deallocated when you go out of scope. As the scope, you know, we had those curly braces, and that is the scope. So whenever you have defined a new variable index inside a scope, the memory gets allocated in the stack. The moment you go out of scope, immediately the memory gets deallocated. So it is automatic allocation and deallocation. Then we have heap. Heap allocation, you have to do explicit allocation, explicit deallocation. So you have to write code in order to do allocation and deallocation. So that heap is requested by a program using malloc or new. New is in Java, malloc is in C. So you do malloc or new, whatever you want to do. You have to explicitly deallocate it using free command, right? So now if we go and look at this code, we would want to argue what type of memory allocation it is. So what type of memory allocation is this one? Yes?
Goes into the RAM.
It's going into the RAM, that is global data allocation, right? This is global data allocation. Now you come here, what type of allocation is this?
Stack.
It goes into the stack because it's a local variable. What about this?
Stack.
Stack. This one goes to heap. So whenever you go to heap, then what you have to do is you have to specify how much memory you want. Right? However much you want, that only that will be available. So there are many different types of memory errors that we'll talk about. Now we'll talk about two. There are many other kinds of memory errors. So the two things that we'll talk about is dangling reference and garbage. So what is a dangling reference? Dangling reference is reference to a memory address that was originally allocated, but now it is deallocated. So in your code, you already deallocated the memory, but you still want to access it. Right? If you still want to access it, then that, or if you still can access it using some variable notation, then that type of pointer or that type of reference becomes dangling. It's called dangling reference. Right? So you already deallocated, but you still try to access. Now garbage is what we saw before. Garbage is memory that has been allocated on the heap and has not been explicitly deallocated, yet is not accessible by the program. So the example that we saw, we did malloc, we allocated memory, but we didn't deallocate it using free, and we can't even access it. So this is a part of program memory, but it cannot be accessible. Right? So that is garbage. So let's see an example of this code. So whenever we have int star dangling, we have to allocate it in heap. This is the pointer. So then dang becomes foo. So foo also returns a pointer, right? So foo is returning a pointer. So what does foo do? Foo makes x equals 100 and it returns %x. So what we should do from here on is we should, okay, before doing the box and circle diagram, let's try to argue intuitively what happens. So now x, it returns the address to x. Now the moment you come out of this function, what happens to that address? So first of all, before even going here, it's when you execute this function, where is this memory allocated? It's allocated in the stack, right? Now you are returning the address of the stack. You go out of scope. This function ends. You go out of scope. Immediately, what happens? The stack memory is deallocated. So this ampersand that you send, %x that you send back, that address is already deallocated. Now you make dang equals that address, and you try to print out the address of dang and the value of dang. So this pointer is already deallocated. Somebody else is using it. So this type of reference is called a dangling reference. Right? So what do you expect to be the output? What would you expect?
Well, dang, now that is like, I mean, the former, what it was.
So you won't get a segmentation fault. Well, you can in certain compilers. If the compiler knows that this is a dangling reference, if it has that module that to understand whether it is a dangling reference or not, it might throw segmentation fault. But what you should see is some garbage values, unless that particular stack memory is not used. If that particular stack memory is not used by any other program, then you should see an output of 100 here. Do you understand what I'm saying? So what is happening is that you in foo you made x equals 100 and you returned the address. Now that memory got deallocated. So what happens when a memory gets deallocated? The operating system just marks that this memory is deallocated. That is one way. The other way is the operating system comes in, makes the memory deallocated and makes the value 0 or some garbage value. That is another way. Depends upon what the operating system does. So if the operating system does not do anything, it just makes that memory address free. Anybody can write on it, but did not change anything. So if any other process does not write on that particular memory, then that value 100 will stay there. Nobody will change it. So if you now do this printf statement, you might be in luck and get that value 100. Right? Depends upon if any other process has executed and used that memory or not. Right? So everybody understands this, or do I need to explain again? So you don't know what is going to happen really. It depends upon other processes. Now you execute the function bar. You execute the function bar. So what is happening is that you have int y equals 10,000. So where will this go? The y?
Stack.
It goes into stack. In z equals 0, where does it go? To the stack. You print. What will you get? 10,000, right? Now you again do printf %p %b tag and start n. So this is another dangling reference that you're doing. What values should you get? So remember, now you have executed bar which used the stack. So since this stack memory was deallocated, the stack that foo was using, since this stack memory was deallocated, bar can now use that part of the stack, right, and put y and z there. So now when you are referencing to that particular stack, you might get any of these values, 10,000 or 0, depends upon how the stack is being used, right? So let's see, what do we get? So when we run this, it gives a warning. It gives a warning that the function returns address of a local variable, but it still runs. What we get is initially we get the address. So this is the address of the stack, right? This is the address of the line of the stack, and we get the value 100. So that means even if it was deallocated, since no other program ran, so we get that stack address, and then the value was still 100 there. Right? Nobody changed. So we got 100. The next time we run, we get this 10,000 and 0. Why? 10,000 and 0 we get because of this print, right? But the more interesting part is the next print. Next print, we get the same address of that stack, right? That stack line, but then the value of that pointer became 0. So we are getting basically the value here at z. We are getting the value of z. Now remember, once you get out of bar, you still deallocate, and you still deallocated the stack. So this is still a dangling reference. And what value we got was the value of z. Now why does this happen? Why did we get the value of z? Depends upon how you operate the stack, how the program is operating the stack, what is it putting in the stack. So again, reiterating, let's go over the program again. Yes, so let's go over the program again. Now, and let's go over the program and let's try to understand how does the stack operate. Now, we will also see this later. So I'm thinking whether to discuss now or not. Let's see again. Okay, so whenever we do int star DAG, right, this is placed where? In the stack. So you have a address and you say that okay, this is for Dan. Now Dan does foo, so you go to the foo function. When you go to the foo function, what do you do in the stack? What happens? What do you do when you do function call? You push the program counter and then the status register into the stack. Did we talk about that in this class? Oh, I'm totally confused now. Okay. So you do two operations. You push the program counter and you push the status register into the stack. Then you put the arguments into the stack. Now since foo does not have any arguments, you don't put anything into the stack. So now you go into the function foo. So when you do function foo int x equals 100, so x, now the top of the stack has x, right? Top of the stack has x, then the next has the program count, the next has the status register, and then the next has the program counter, and then it has DAG, right? So at the top of the stack you have x equals 100, then you have program counter, then top of the stack you have x equals 100, then you have status register, then you have program counter, then you have DAG. So now x equals 100, you return the address of that x, so that top of the stack. So if top of the stack was 4, let's say the number address number was 4, then the next address was 3, so in 3 you have status register, next address is 2, there you have program counter, and then the last address is 1, you have DAG, right? So now if you do DAG equals foo, then DAG will have the address 4, and in the address 4 the value is 100, right? When you come back, what do? Foo has return function. So when foo has return function, it deallocates the address 4. That is the operation of the return function. Because you know, whenever you return from a function, there has to be an assembly code that runs, the RET assembly code. When you run the assembly code RET, it deallocates. One of the functions that it does is that it deallocates the stack. So now the top of the stack, instead of being 4, is now 3. Right? Now when you come back, what operations do? You pop the stack, put it into status register, you pop the stack, again put it into program counter. So once you pop the stack, the top of the stack goes from 3 to 2, and then it goes to 1. Right? So now in the stack you just have the DAG. Right? So when you have that, you print what happened? Oh. So you print DAG. Now DAG, what was the value of DAG? It had the address 4. What was there in 4? When we deallocated, we didn't change anything. The value at 4 was 100. Right? The value at 4 was 100, so we have the value 100 here. Then you execute bar. So now remember, the top of the stack is at 1. Right? When you execute bar, what happens? You push the status register. So it becomes, no, you first push the program counter. So address becomes 2. This you have program counter. Then address becomes 3. Push the status register. You have the status register there. Then in bar you had y, int y, right? So you have to have a new address. So now the address becomes 4, and in 4 you have 10,000. Then you again do int z. You have a another stack value, right, in z, and you have z equals 0. So now at address 5 you have z equals 0. Now you are calling printf. This is another function. What do you do when you have this function? When you have this function, one of the things that you do is you push the arguments of that function in the reverse order, right? You push the arguments of the function in the reverse order. So first you push z and then you push y. So when you do that, then what happens is that the locations of z and y just switch. Right? So now z comes into the stack pointer 4, in the stack address 4, because we have called printf. So z is in 4, or y is in 5. Come out of printf, deallocate. Again come out of bar, deallocate everything. So again all the addresses, now your top of the stack is just 1, but nothing changed. So in 4 now you have z, because you have called printf and you push the variables in the reverse order, right, into the stack. So now z is in 4. So whenever you call dan, you'll get the address 4, the same address, but the value of dan will now be 0. Right? So that's why you get such an output. Now the thing is, this will become much more clearer when we talk about runtime execution. Right? That is the last thing that we'll talk about. So if you have doubts now, hold on to that. Maybe next week we'll discuss it. So that's why we get that output 0, right? Now in some other compiler, so this is in GCC, right? In some other compiler, it also gives a different kind of warning. Right? What it does is that it says the address of stack memory associated with the local variable x return, and this warning, it's just a warning, so it does not stop. And when you execute, you get a different result. You get a different result. Why do you get a different result? See, the address is the same. Top of the stack, the address is the same. But now instead of getting 0, you got 10,000. Why? It depends upon how you deallocate. So remember, when we talked about printf, we said that y and z are switched. Why they can be switched? So there can be two policies that an operating system can take. First of all, remember, int y equals 10,000, int z equals 0 were local variables in bar. So in address 4 you had y, in address 5 you had z. 5 was the top. Now there can be two strategies in calling printf. One strategy is, whenever you call printf, you remove those local variables y and z, replace them with the arguments of printf. That is one policy. So if you do that, you remove those local variables, so then the top of the stack becomes 3 because you remove them, and then you push the arguments of printf in reverse order. So z comes at 4 and y comes at 5, right? That is one thing that you can do. The other thing that can be done is that you don't remove the local variables y, z. You don't remove the local variables. You just push y and z again into the stack. So if you do that, then what happens is the z is at memory address 6 and the y is at memory address 7. Do you understand this? Because the top of the stack was 3 when bar executed. Then bar declared y, so y came at 4. Again declared z, z came at 5. Then it has to push all the arguments in the reverse order. So z came in at 6, and y came in at 7. Now when it comes back from printf, you lost the scope. So if you lose the scope, you have to pop the arguments of printf. You have to deallocate the memory. So then y at the top of the stack from 7 went to 6 and then went to 5. Right? The top of the stack went to 5. In 5 we had z, and in 4 we had y. Right? Now again, when you come out of bar, the scope got deleted. So your top of the stack came from 5 to 4, then 4 to 3. Then you pop the stack and put it into put it into status register. So from 3 you came to 2. You pop the stack, put it into program counter. From 2 you came to 1. Now remember, nobody changed the stack. So in 4 you still have y. In 4 you have y, in 5 you have z. So now you print dang again, dang points to 4, so it gives you the value 10,000. So it depends upon what policy the operating system is taking to manage the stack. Right? It totally depends upon the runtime environment. So that's why when you have dangling pointers or dangling references, you get totally different results in different systems. In one system you get the result this and 0. In other system you get the result some address 10,000. So when you have dangling references, you have all your execution patterns. So do you understand this? Or do you have to go again? Anybody has doubts in this? Understanding dangling references. So again, reiterating, what do you mean by dangling references? Dangling references means you have a means to go to that same location, but that location is already deallocated. Right? So you are accessing a deallocated location. In that case, you will have totally wrong results. Now let's take another example. This is another example of dangling reference, right? So here in main you have dang and foo, then you do malloc, so then you get a location in the heap, right? Now you made foo equals dang, so which means you pointed foo, so foo, now star foo becomes star dang, right? So when you do star foo equals 100, so basically your star dang becomes 100 as well. Now you do free foo. So when you free foo, what are you freeing? What memory location are you freeing?
Some address that
Yeah.
it's the same address that Dang shared.
It's the same address that Dan was pointing to. So the new memory address which you got by doing malloc, that got free. So that got deallocated. Now if you do star Dan, Dan was pointing to that. Dan is still pointing to that free deallocated memory, right? So that becomes a dangling pointer. Still trying to access that memory. Now you go and say foo equals int star malloc size of int. So now what happens? Now you have another new memory, and foo points to that memory. Right? You made star foo equals 42. Where is dang pointing again? Pardon?
Same place.
It's the same deallocated memory that is pointing at, right? So you do foo is int malloc this, and you make star foo equals 42, and then you free foo again, and you print dang. Still dang is a dangling reference. So what value should you get? It's very tricky. You again, depending upon operating system, you will get two different values. So let's see whether whatever value we get, can we explain it? Can we explain it somehow? What is happening? So we run this. There is no warning at all at this point. There is no warning when we compile. The output that we get initially is the value of dang is 0. And then the second output that we get is again 0. We run it again in a different system. What the first output we get is 100, the second output we get is 42. Now how can we explain this? How do we explain this? First of all, let's try to explain this 142. No. First of all, let's go and explain the 0. This explanation is very easy to do. What is the reason? The reason is whenever you are deallocating that memory to which DANG is pointing, fine. But you have deallocated the memory. What the runtime executions module of the operating system did was went into the deallocated memory, just wiped it off, made it 0. Right? That's why every time you access star DANG, although it's the same memory that you're accessing, the value is 0. Because it has been deallocated already. Right? So that is why you get 0. This is for that particular machine, that particular runtime environment. Now you go to different runtime environment, you get the value 142. How can you explain this? We can explain this using a box and circle diagram. Let's do this. So how can we do this? So whenever we have int DANG, so for DANG we have to have a box and circle. Right? For DANG we have it, and also for foo. Now we did DANG equals int star malloc. So we have another memory location. Let's say this is 0x4, and the moment we do that, then this becomes 0x4, and we have this. So this is star DANG. Now we made foo equals DANG, which means what? If we do foo equals DANG, how will it look like? So 0x4 goes here. So which means what is star foo? This is star foo. It's pointing to 0x4. Whatever value is there. Now we made star foo equals 100. So if we make star foo equals 100, what will be 100? 0x4 will have the value 100. Right? It will have the value 100. Now you do free foo. If you do free foo, then one operating system or one runtime module of operating system can do this. It just delinks. Right? It just delinks, and it just doesn't give any address here. Right? And it doesn't change the value. It doesn't change the value there. So DANG is still pointing to 100. Right? Still pointing to 100. So when you printf DANG, you'll get the value 100. 0x4 is deallocated, but you didn't change it. You didn't change the value. Right? Now you do foo equals in star malloc. This memory was deallocated. So what it means when it is deallocated, that means it's free for anybody to use, right? So now what the memory management system does is that, okay, this memory is free, the next code is foo is in star malloc size of int, so why not use this memory? So what this code does, then it again puts the value 0x4 here. So now we have another link to the same memory location. You do star foo equals 42. What will happen? What will happen if you do star foo equals 42? 100 changes to 42. Remember, dang is the still dangling reference to that particular location, 0x4. Right? Now you free foo. Again you free foo. So if you free foo, then again this link gets cut and this changes to 0, or basically null. You make it null. Yes.
I'm confused as to when 0x4 was initially deallocated.
Initially deallocated when you did the first free foo. Remember, you did free foo after making star foo equals 100.
But if 0x4 is star foo, why wouldn't the foo block be the one that's deallocated versus the one that's star?
No, so that is what the free function does. Free cannot deallocate this because this is a local variable, right? Free only deallocates what in the heap. So that is in heap, right? So this one is in heap. Heap memory. So free only deallocates memory that has been allocated in the heap. Yes.
So how do we know the second allocates the same address?
You don't know, it might.
So it might not change the 100 value after all.
Yeah, it might not. So it depends upon the runtime execution module of the operating system. Yes.
Are we going to have this in the past? Because they have different results.
So I'll ask you what different results you can get. No, I won't ask you what different results you get. I'll give you a result and you will have to explain how you got that result. Right? So I'll give you a possible result. So yeah, so then what happens after you do free? That particular memory is again deallocated, but still dang points to that memory. It's a dangling reference. So now when you print dang, you get the answer 42. Right? So that's how you can get 142, depending upon different machines. Depending upon different machines. So that is an example of dangling reference. Now let's do it again. Oh no, let's try to analyze this code. So no, before we go into a different topic, yes, you have doubt.
Okay, so I understand that the 0x4 gets deallocated to free foo, but then how can star dang print 100 then if that's been deallocated?
So even if that particular memory is deallocated, the value at star dang is still the address 0x4, and that address is there. Deallocation doesn't mean that you destroy that address, right? So that address is there. So that address is there. What does deallocation mean? Deallocation can mean many different things to a runtime execution module. One thing that it can mean is that any other line of code, if it wants to allocate a memory, this particular memory is free, right? So you can use that memory. So that doesn't mean that I will just burn out that address and never allow any other process to use that, right? So it means that I will still, you have the same address 0x4. Some other line of code, if it wants to take that address, it can take it. So if you still have that address 0x4 and you have that address inside dang, so dang still points to that memory line, right? And what value does it have? You don't know. It depends upon runtime execution engine. So it might change it to 0, or it might keep whatever value was there, or it might just have some garbage. You don't know. So that is why when you have dangling reference, you have problems. You have inconsistent results for not only different systems, But also if you are using concurrent programming, no, that won't affect. No, so you have inconsistent results when you use different systems. That's what happens when you have dangling references. So anybody has problems with this? Okay, so everybody understands. So what we will do now is we will try to analyze another code, right? We will try to analyze this code. So this is the method that we'll use in your exams also to ask questions. So whenever we have that notation, that comment memory 1, that means you can take whatever heap allocation was there, you denote the address as memory 1. So you denote the address as 1, right? That is the convention we'll follow. So whenever we have in malloc we have / memory 1, that means that particular memory location has the address 1. Right? Same for memory 2 or memory 3. Now we have this kind of 0.1, 0.2, 0.3, right? So what we'll do is we'll use these comments to ask you questions. So 0.1 means you execute up to 0.1 and you show what is the box and circle diagram after you have executed just the line before 0.1, right? So you execute star a equals 42, and after you have executed star a equals 42, what is the status of box and circle? Right, so that is what we want to ask you. So then when we reach 0.1, we'll ask you which ones are the dangling pointers, which ones are the LISs, and so on. Right? So you will only consider the box and circle diagram up to 0.1. Right? You won't execute any further. Same for 0.2. So you execute up to 0.2, do not execute any further. Tell us what are the LISs, dereference, or dangling references, and so on. And 0.3 as well. So let's try to do this one on the board. I think I have the solution. Yes, I have the solution in the slides. Okay, so let's start. So we have int star star q, right? What do we do? First of all, is what type of allocation is this? Is this stack, heap, global? What is it? Global. So it goes in the rank. But since it's a declaration, we'll have to have a box and circle diagram for it. So we have a box and a circle, and we call it Q, right? Then we come to main, and inside main we have int star a, right? So what happens? This goes where? A goes where?
Stack.
Into the stack. So this is a stack allocation. A. Now we have a. Oh no, we also have int star b, right? We have int star b. So if we have int star b, then where does it go?
Stack.
Goes to the stack. Now we have a equals int star malloc size of int. Is a in scope?
Yes.
It is. It's in the curly braces. So you can write that code. It won't say out of scope. So if you do malloc, then what do you have to do? You have to allocate it in the heap. So let's say this is our heap space. So you have to allocate some memory in the heap space, and let's say that address is 1. address is 1, and since you did A equals that, then this A became 1 and star A points to that address, right? Then you did again you did B equals in star something, and you made it memory location 2, and this will be 2, and star B will be here. So now you do star A equals 42. What happens?
The value for star A becomes space 1 gets value.
Space 1 gets filled with 42. So in this point 1, so here we stop. This is our point 1. Are there any dangling references? Are there any aliases? Nothing. Okay. Then we move on. Now we do B equals in star malloc size of int. So if we do size of int, then or if we do malloc, then we have another address 3. Now B became int star size of int. So what B was previously that. So now what will happen?
Change 2 to 3.
Instead of 2, B will have 3. B now has 3. So star B gets delinked. Now star B points to 3. Right? So that 2 can be deallocated, but it hasn't been deallocated yet. Is it deallocated? No, because we have to explicitly do it. This is heap allocation. Now we do star A equals, star B equals star A. What will happen? Star B equals star A.
The value for star B equals 42.
The value for star B becomes 42, which means which one becomes 42? 3, right? So star A was what? Star A was the value inside this 42. So you put it into the value in the location associated with star B. Location associated with star B is number 3. The value becomes 42. Now you do Q equals ampersand A. What will happen? Q equals ampersand A.
Q becomes the value 1.
Q becomes
The address of it. Yeah, the address of that.
the address of A. So let's say this one is our ampersand A, this one is ampersand B, and this one is ampersand Q. So value of this becomes ampersand Q. No, A, sorry, ampersand A. So if that is the case, then what is star Q? Pardon?
1.
No, the arrow. Where does it point?
Oh, the box.
Box 1.
The box of ampersand A.
The box of ampersand A, not the box 1. Because it's ampersand A, so this location is ampersand A, not that one.
Oh.
So Q now points to this. So this is star Q. This is the location associated with star Q. Everybody understands? So that is our point 2. We stop here. This is our box and circle diagram for this point. Now, which memory locations are deallocated? None of them are deallocated. Because heap, we haven't have any free commands. So if there is no free command, then heap is not deallocated. We are in scope for everything, so none of the local variables are deallocated. Global variables cannot be deallocated, right? So nothing is deallocated. Is there any dangling reference?
Yes.
Where?
No, because nothing's been deallocated.
Nothing has been deallocated, so it's not dangling reference. There's no dangling reference. Is there any garbage?
Yes.
Which one?
2.
2 is garbage. Why? Because you did not deallocate it, and also you have no way to point to it. None of the, you cannot do any star. Star B does not point to it. Star A does not point to it. Star Q does not. Star Q does not. Star A is not possible because according to definition, star B is not possible. So you cannot point to 2. So that memory location 2 becomes garbage. Now we go on. So now we execute and the curly braces are closed. So we get out of that scope. If we get out of the scope, what happens? A and B, is A deallocated? A is not deallocated. So what is deallocated? B. Only B is deallocated. So B is deallocated here. B is deallocated, A is not, right? A is still there. So at this point, only B is deallocated. Any other deallocations? No. Is there any other? Any dangling reference? No dangling reference. Any garbage memory?
Yes.
2 and 3. Right? You cannot access 3. Yes.
How did B become deallocated? You said something about going out of scope.
Yes, just by going out of scope.
4.3.
Yes,
Okay.
for point 3. Yeah.
One thing, if A was declared before that, you know, the curly brace, are we able to visualize it within that block?
Yes, well, this is still in scope. Inside the curly brace, so what is the scope of A? The scope of A is the main curly brace, and scope of A ends here in this curly brace. So whatever is inside, you can still do it. Even if you have multiple curly braces, you can still access it. That's the static scoping we are using. So now 2 and 3 are garbage data because there is no way, you haven't deallocated 3, you haven't deallocated 2, but there is no way to access them. Right? So 2 and 3 becomes deallocated. There is no dangling reference here. So I think that is what I have in the rest of the slides also. Again, we are at a point where we don't really have time to start a new topic. So, okay, do you have any questions? Do you have any questions regarding assignments and the content? If not, then you can go. We'll continue from here next time.